Hello and welcome to the 37th lecture. So today we're going to do some questions from the practice exam for midterm 3. Okay, there are many questions. We're only going to do a few of them. I'm selecting questions that I think might be the ones that give you the most difficulty, that are also most likely to come up. So let's start with question 4. Okay, so this question is testing your understanding of the fundamental theorem of calculus part 1. So recall that briefly. If we have some function f, and let's say it's defined from a to b, let's make it a positive function for simplicity. We can define this thing, which I call the increasing area function. It should better be called increasing signed area function because it doesn't have to be positive. We define it like this. This is f right here. And the main part, the heart of the fundamental theorem of calculus, is just that this thing is an antiderivative of f. And that follows very easily from the pictures that if we just move this forward a little bit to x plus h, and we look at this strip right here, then this strip is like g of x plus h. Well, it's exactly g of x plus h minus g of x. So if we divide by h, that's like dividing by the base of the strip, right? So this is like the area of the strip divided by the base of the strip is basically going to give us the height of the strip. And the height of the strip is basically f of x, right? So that's why this is true. Yeah. And it's the heart of the fundamental theorem of calculus. That's the main thing that makes the fundamental theorem of calculus work. And we need to test it because it's such an important principle, but we can't just ask you to differentiate a function like this because it's too easy. So there has to be some way that we mix it up to make it a bit harder, and the standard way is to create something like this. And there's only one trick to remember to answer a question like this, and that's to formulate this guy that we can't differentiate straight away as the composition of two functions that we can. Yeah, so this stuff here is all recall. Put that in a box. So for this guy, since I used G already, let's call something h. So let h of x be the integral from 0 to x of cosine of pi of t over 1 plus t squared dt. Yeah? And then we see that f of x is just h square root of x. Yeah? And then you should feel pretty good because we know the derivative of h, it is just increasing area function. Put it over here. So h prime is just a function in the center, right? H pi of x over 1 plus x squared. Yeah? And by the chain rule, if we want to differentiate f, then it's the derivative of the outer function times the derivative of the inner function. Yeah? And we want this as a specific value. We want this at 1. So it's h prime of 1. And then this will just be over 2. And then h prime of 1, we just put directly what 1 is inside this. Let's put it down here. So cosine of pi is minus 1. And then this is 1 plus 1, which is 2. So this is just getting minus 1 over 4. Yeah? Cool. That's the main thing. That's the main trick. So this is extremely likely to be tested because this is such an important thing, as the name suggests. And there aren't that many ways to test it. One of the other ways to test it is to create a function like this, where we integrate, let's call this thing w of x. So we could do something like this, say square root of x to x squared of something, whatever, say t to the 3 dt for x bigger than 1. Yeah, and then we notice that this guy x squared is bigger than square root of x for x bigger than 1. So what are we going to do? We draw a picture. Here we have square root of x. Here we have x squared, right? So then w of x is the integral from 0 to x squared of t to the 3 dt minus the integral from 0 to square root of x t to the 3 dt. And each of these guys you can differentiate just using the method above. So we can break down this harder looking problem into just the difference of two easier ones, and it's just this picture, right? So we have the integral from whatever, from 0 to x to the x squared, and what we're interested in is this area. So we take the integral from 0 to x squared, and we subtract the integral from 0 to square root of x, and we get exactly the stuff that we want. So it should be clear from this picture that this thing is the same as this thing, and then we can just do it, right? So if you keep a clear picture in mind of what this means, then this decomposition should come up pretty easily to you, or pretty easily for you, and then we can do these kind of questions. So this is the harder manifestation of that kind of a question, but that's more or less the only things you can see. So be ready for this. It should be not too difficult. Okay, let's do another question. Net change. This is question 5. A bacterial colony, I'm abbreviating, grows at a rate of e to the 3t100 a day. Find the increase in population over 4 days. Okay, so solution. So the fundamental theorem of calculus is this, right? We can calculate any definite integral just by finding the antiderivative, capital F, any antiderivative. And we get this, right? That's the power of it. We just need to find the antiderivative, and then we can just, any antiderivative, and just stick the endpoints in, and we have the explicit definite integral. Okay, so we can also rewrite this like this. And we discussed various ways where this makes sense to us. For example, if we are integrating up velocities that change over time, then the integral of the velocities will exactly be the total displacement, yeah? Where we are at b minus where we are at a. Yeah? Okay, so this question is testing understanding of the fundamental theorem of calculus. It's about something which is changing. We have the rate of change, yeah, which is given to us here. And we want to know the total difference of this quantity over some period of time. So in this case, let's call, so say this is a recap. This stuff is a recap. Okay, recap, So let P of t be the population at day t. Yeah? And the information we're given is that it grows at a rate of E3t 100 per day. So I'll write that like this. Oops, e to the 3t. So it's growing exponentially, which is actually what it will do. Well, it's actually growing fast and exponentially since the derivative is this. Nevertheless, we have this rate of change, yeah? And then we just apply our theorem, which is right there. Because what we want to know is how much this population grows over 4 days, which is whatever the population was at day 0. Start again. It's whatever the population was at day 4 minus whatever it was at day 0. So write that down, language of math. It's this. And we are given, we're just stating the theorem here, and we are given what this is. And then we just can calculate this integral. We can find the antiderivative of this, right? This is the antiderivative. And then we just put the numbers in. So we're going to have e to the 12 minus e to the 0, which is 1 over 3. And that's it. So 4 days after we start, we have the population has grown by e to the 12 minus 1 over 300 bacteria. Easy. Well, easy if you recognize that this is a statement that you can easily answer with the fundamental theorem of calculus if you've understood the fundamental theorem of calculus in this formulation of the net change theorem. Okay. I'm going to raise the board and then we'll do question 11. Question 11. We have this and this is given to us, and the question is find integral from 1 to 5 to f of x dx, and then find the integral from 7 to 5 f of x dx. Okay, so as always, we're going to draw a picture, and that'll clarify for us what's happening here. So we have 1 to 7. Let's draw, for simplicity, this as a positive function, so whatever it's doing, something like this. Yeah? And the information we're given is that this area underneath the graph is 12. Yeah? And we're also given the information that the integral from 5 to 7, which is this stuff, so this is 5. So this stuff has got area 3. Yeah? And what we're actually interested in is the integral from 1 to 5, which is this stuff here, which I'm going to outline in green. This stuff here. Yeah? And as we see from the picture, clearly this stuff here, let me maybe do a crosshatch on it. This stuff here is the same, is equal to the entire stuff underneath the graph from 1 to 7 minus the stuff underneath the graph from 5 to 7. Yeah? So all we need to do is take this quantity and subtract this quantity to get this quantity. Yeah? If you draw the picture, you can't go wrong with this. Yeah? If you think about what this means as a picture, this is straightforward. And that's what I want you to do. I don't want you to be applying rules that you've memorized. I want you to be doing what this is. This is, amongst other things, a language to describe pictures. So we get the information in the language, we draw pictures, and then it's clear what to do. Huh? So here we go. We have 1 to 5 fx dx. And that is equal to go from 1 to 7 fx dx minus the integral from 5 to 7 fx dx, which is drawing what we've learned from the pictures, and we put the numbers directly in. So this is 12 minus 3, which is just 9. And we have a 2 here. No? It's just a constant. We can pull it out from an integral because, again, a sum. So again, an integral is just a sophisticated version of a sum, right? And all the algebraic rules that you know for sums are true for integrals. So you would have no issue doing this. If you had 2a plus 2b, for sure you know that's 2a plus b, right? That's a rule you know for sums. So the same is true for an integral. Yeah? So we just pull out this 2, and then we have that this thing, 1 to 5, 2 f of x dx is just equal to 18, right? Just write it explicitly. And that's it. So this question is just testing your understanding of these basic properties of integrals. This guy, 7 to 5, when we have the larger number underneath, we define this to be equal to minus when we put the larger number on top. So this is actually just defined to be this. For our purposes, there's a deeper reason why this is the correct way to think about it, but for us it's good enough. We just define this thing to be equal to this. So whenever you have an integral, a definite integral with the bigger number on top, just flip it around and put a minus sign, and that's what it means. And that's what's already given to us. It's given us, so it's just minus 3. Okay, so not too bad. Actually quite straightforward if you're drawing pictures. Okay, this is another question that often throws people. Question 12. And this kind of question is pretty important for the volume kind of question that we were, volume kind of sections that we were doing. So this is actually 12b. We can do 12a as well, but 12b is the one which typically people find harder. So we have this thing. The limit as n goes to infinity of the sum from I is equal to 1 up to n of 1 over 1 plus 2i n squared times 2i n 2 over n. And then it says, express this as a definite integral. And it even tells us over what, so we can figure it out, as I'll show you. Over 0 to 2. Okay. So, this is testing our understanding of Riemann sums. Huh? So, what are we going to do here? Well, what are Riemann sums? So, I'm going to, for convenience, draw a positive function. So, if we have some integral from a to b, then we've learned that the definite integral is what we get by taking the limit of Riemann sums. And Riemann sums, when we cut this interval into subpieces of equal length, and then we define rectangles above each interval. And the rectangle will be defined by the function itself, and we're going to choose to define the height of each rectangle either by the right endpoint or the left endpoint or some other point, a midpoint sometimes. And most obvious and typical thing is to do the right endpoint, which kind of looks like this. Like this. That is what a Riemann sum is. And in order to do this, we have to sort of develop this machinery, right? So recall, we have to develop these intervals. We have to find a way to describe them. So if we cut up the base into n equal subpieces, then we let delta of x be the length of this interval a to b divided by n. We let x0 be the leftmost point, and then we keep going along, defining each guy from the last guy by adding delta. And then so xi plus 1 equals xi plus delta for I. Let's raise that. For I is equal to 0, 1, to n minus 1. Yeah? That's what we did. Yeah? And in particular, from this, it easily follows that xi is just equal to I times delta of x plus a. These are things we talked about a fair bit. If you have a bit of experience computer programming, this will be defining things iteratively this way and drawing this more general formula. This will make more sense, as will the overall procedure. Yeah. So if we do it this way, then this thing here is x0. The next guy is x1. The last guy is xn. And if we do the right endpoint approximation, where we're defining the height by the right endpoint of each interval, then the first rectangle will be given by this. So let's put it over here. So the first rectangle will be f of x1 times delta of x. The next one will be f of x2 times delta of x, and so on. And the last guy will be f of xn times delta of x. Yeah. Again, we have the pictures, and what we're doing here is describing them in this language. Yeah? The pictures are the real thing. This stuff exactly describes what we're doing. This is the area of all n rectangles I just drew. Yeah? Cool. And we know that this thing, which we can express like this, the sum I equals 1 up to n, f of xi delta of x, we know from this picture that as the size of the rectangle's base gets smaller and smaller, it looks more and more like the area underneath the graph, or the sign there underneath the graph. We have a function that changes sign. So this thing goes to the integral from a to b. So that's a quick recap on Riemann sums. Okay, cool. Now, we look at this thing. We identify, first of all, what the delta of x is. It's going to be 2 over n. We already told the interval is from 0 to 2, so it has length 2. Yeah? So from this thing, so all that stuff is recall. From this thing, we see that, let me change pen. We see that delta of x is equal to 2 over n. Yeah? And then what would with breaking this interval from 0, 2 into n equal pieces with this delta of x, so the first guy would be 0, and then the next guy would be 0 plus 2n, and then so on. So the ith one would be 2I over n. Yeah? Exactly what this thing tells us, because in this case, a is equal to 0. Yeah? The endpoint of this interval is 0. So that's our xi here. That's our xi. Yeah? So with this knowledge, we can rewrite this thing if we wanted to, replacing this 2 I over n with just xi. Yeah? Why not do that? That's cool. Let's just do that. So star is equal to the limit as n goes to infinity of the sum I equals 1 up to n of 1 over 1 plus xi squared times xi. Let's put it up here if we wanted to. Yeah, this is xi as well, and then times delta of x. Yeah. And then now what? Well, now this thing here for each n is representing the sum of these n rectangles. Yeah? Yeah? So each individual expression is the area of one rectangle. Yeah? And the rectangle's got base delta of x, which means that the height of the rectangle has to be this thing. Yeah? Height of the rectangle has to be this thing. So let me write that. So each rectangle has area given by xi over 1 plus xi squared delta of x. Yeah? And so height is defined by this thing here, because that thing is the base. Yeah? So we've broken up this interval 0 to 2 into these individual pieces like this. This here is xn, right? The base is delta of x, and the height of each rectangle is given by this thing. Yeah? Should be therefore clear to you that the function that we are approximating the area underneath the graph of therefore has to be yeah. And indeed, if we define the function like this, then this thing would look like just the sum I equals 1 up to n, f of xi delta of x, and then by this general stuff we just discussed, it tends to the area underneath the graph of the function f, which is this thing. Yeah. So this is for me just exactly using the language to describe pictures. So if you believe me on this, if you start to feel this way, I say this way because this is the way. If you start to feel this, then this stuff should be straightforward. But this creates a lot of problems for people because as I said in the introductory video, for historical reasons, math is taught as a vocational profession where you simply are taught to perform algorithms and memorize steps. And many people, and I included, went to high schools where that's exactly what we learned, and come to university looking for algorithms in a math class. So I often encounter this where I'm trying to explain something, and the student I'm talking to goes something like, so I do this, and I put this into this, and put it into that. And what they've extracted is the steps that I just did, but nothing about why. And you can perhaps get a passing grade on the first couple of midterms, maybe if you're very good at that and you memorize the steps very carefully and memorize slightly different questions as different algorithms. But it falls down at stuff like this. If you don't think about what this stuff means and you're trying to just apply a procedure that you've memorized, then it's very easy to get this wrong. And conversely, if you think about what this means, it's impossible to get it wrong. So please trust me on this, that memorizing steps is ultimately going to hurt you in your further study of anything, actually, but most of all of math. So don't try and do that for this kind of thing. Use what we use what this language is for, which is to describe these pictures, and be convinced that this thing represents the area of all of these guys. Each individual expression is the area of one of those guys. And then something like this, as difficult and ugly and complicated as it looks, won't be, because you know what this actually means. You know this is just adding up a bunch of rectangles, each one of which has got a base length of 2 over n. And the sum of all those rectangles is going to approximate the area underneath the graph of a function, and that function defines the height. So that part is the part where the function is, and that's how we ultimately get to this. So if you're finding this thing difficult, it's probably because you're trying to memorize steps. And please stop trying to memorize steps. Please do it the way I'm trying to tell you. Right at the end, it's the end of the course, but most of you are going to want to do calc too. Just trust me on this. Just trust me. All right, cool. I'm going to raise the board and we'll do another question. Okay, we're going to end with an optimization question. So there are like 4 optimization problems on the practice exam and a couple of graph sketching questions. So there's a good guess that those will be our free response questions that will have 3 times the weight of a multiple choice question typically. And it is. Did I miss some other topics? Probably there's some other topics that could be free response, but those are with high likelihood. So it's very good to get good at them. Graph sketching is harder to do online. I don't know how the examiners will come up with that, but optimization isn't. I mean, that's something we can formulate online, so it's a likely question, and there's lots of practice exams, and it's one of the main things that we've learned since last semester. It's also a topic that's super important for the reasons I said when we talked about it. So the question I'm going to do is the one which is perhaps furthest away from anything we have done, which is this ellipse question. So this is question number 21. So the question is, find the points on the ellipse and the ellipse is given by 4x squared plus y squared equals 1 that are furthest away from 0, from minus 1, 0. And then what is that distance? Okay, so solution. First thing is to draw a picture. So you should all be happy with the equation of a circle. This looks a bit like it, but it's not actually a circle, it's an ellipse. And we figure out its dimensions by sticking in x is 0, because when x is 0, then we're on the y-axis, right? And then that just gives us y squared is 1, so we're going to have plus or minus 1. Let me check that I didn't do this wrong. Yeah, I did do it wrong. It is 4, not 1. So when x is 0, we're going to have y squared is 4, so that's plus or minus 2. And then to figure out where it crosses here, the x-axis, we're going to stick y is equal to 0, because when y is equal to 0, then we are on the x-axis. And then it's going to be 4x squared is 4, which is x squared is 1, so we're going to have plus or minus 1. Minus 1 plus 1. So our ellipse looks like this. That's our ellipse. And So one of the point that we're interested in is actually a point on the ellipse. This is the point -1, 0. Yeah? And as we can see, if we consider other points on the ellipse, then there is a definite distance, and we're trying to find the maximum distance. We can also see this is completely symmetrical. So this distance, we have exactly the guy which is underneath it has exactly the same distance. So we have the same x coordinate, but minus the y coordinate. That distance is exactly the same. So we'll have 2 points that will maximize this distance. And we can also see that we should be able to find it, right? There should be some definite answer to this. Yeah? Cool. So now our job is to turn this stuff written in the language, mostly in the language of words, into the language of maths, so that we can actually apply the tools of calculus to it. And let's think about what are involved. So I've misspelled the word furthest, but less badly than I did in class today, probably. Yeah, but you know what I'm trying to say. So if we're talking about the point furthest away from -1, 0, then we are talking about distance, right? So we're talking about having some choice of point, say x, y, on the ellipse. And what we're discussing, what we're trying to maximize, is the distance between this point -1, 0 and the point x, y. Yeah? And that thing, of course, we can express in the language of math, right? So in class today, some people came up with this. They noticed that we form a right-angled triangle like this. And if we do that, then this length is just the hypotenuse of the right-angled triangle. So we can figure out the sides. And this side right here, what length will that be? Well, it goes from -1 to x. So that length will be 1 plus x. Yeah? And the other side, this side here, well, this will just be y, right? So by Pythagoras, another word I'm going to misspell, by Pythag, distance, so let's denote the distance of a point xy as, say, let's call it s, because we're going to use d later. It's going to be the square root of y squared plus 1 plus x, everything squared. That thing is the length of our hypotenuse. That's the thing we want to minimize as we move x and y around on this ellipse. No? Did I say minimize? I meant maximize. That's the thing we want to maximize as we move x and y around on our ellipse. So this is the distance of x comma y away from -1, 0. Cool. So we're making some progress. We have expressed one of the quantities in the language of math, right? Now we have to try and actually find these points x and y. There's going to be more than one that maximize this. And a couple of things. Well, firstly, with two variables, we have a problem. We don't know how to maximize a function of two variables. That's something you will learn in multivariable calculus. I hope you all do this subject. But this is one variable calculus. Yeah? So that's our first problem. Second problem is we don't like square roots. Yeah? Square roots are a pain to deal with. Make ugly expressions when we differentiate them. And if we're trying to maximize the distance, then the thing that will maximize the distance will also maximize the distance squared. So we could just make our life easier by just getting rid of the square root and talking about the distance squared. So let's just do that to begin with. So this is now the distance squared, but good enough. It's the distance squared. Yeah? Okay, so that's one of our problems. Now back to the other one, that we don't know how to optimize things over two variables, over x and y, but we have to think a little bit more. So this thing is actually a true formula for any x and y, right? This is for any x and y. But we don't care about every x and y. We just want the x and y that live on this ellipse. Yeah? And the ellipse is a one-dimensional thing, right? It's a one-dimensional curve. So it should seem somewhat intuitive to you that we can just use one variable to describe it, or at least describe parts of it. There should be ringing bells to do with implicit differentiation and those topics. Doesn't matter if it doesn't, but we've seen those kind of issues before. Yeah? So if we are smart, then we don't minimize over every x and y. We just minimize over every x and y on the ellipse. But every x and y on the ellipse satisfies this equation, which in particular allows us to locally describe it just in terms of one variable, because we can just solve for x in terms of y or vice versa. Yeah? So we can actually get rid of this thing as a function of two variables, right, as a function of one variable. And that has also the advantage that forces us to be considering the points that we care about, the points on the ellipse. So we can kill two birds with one stone with this by using this constraint and putting it into this formula. And then what we'll have will be the distance of points on the ellipse from our particular point -1, 0. So let's write that down. So we can use equation of the ellipse to solve for, let's do it for y. Yeah. So we're going to have y squared is equal to 4 minus 4x squared. And we could further solve, and there's going to be two solutions. There'll be the positive solution, y is equal to this square rooted, and then the negative solution. So y is equal to plus or minus square root of 4 minus 4x squared. Yeah? And now this is our calculation. Let's go back to the picture and see if we believe it. So what this says is that if we have some x between -1 and 1, yeah, we can actually find the y on the ellipse via this formula. And there's actually going to be two y's given by this. And that's what we believe, because if we have any x here, we can see that there's going to be two y that will correspond to that. And there'll be the y, and then there'll be the negative y, and they'll both be on the ellipse, which is exactly what the calculation shows us, right? So our calculation and our picture are completely in sync with each other. We're going to be doing this dance from the picture to the calculation throughout. That's what we always do. That's the job. That's our business here. Yeah? Cool. So we're feeling happy that this makes sense. Yeah? And now we want to use this. We want to use this to simplify this. Yeah? So let's write d of x, and let's replace this y squared with this thing. So 4 minus 4x squared plus 1 plus x, everything squared. So what is this? This is the distance squared of points x, y, yeah, away from -1, where xy lives on the ellipse. And when xy lives on the ellipse, then we can define it just with the x coordinate, because with the x coordinate there's only two solutions, the up and the down. And for this distance function, because we have this symmetry here, both of them have exactly the same distance. Yeah? So for each x, both those solutions have the same distance, yeah? Which is why we just have one number coming out here. Yeah? So this thing, d of x, is the distance of, I need to draw a bigger picture, I guess. Draw a bigger picture. So for every x, we have that there are 2 points on the ellipse, which are defined by this x. Yeah? This is the x, and then this is the 4 minus 4x squared, and this is the other guy, x, 4 minus 4x squared. Yeah? For every x between -1 and 1, this is definitely the case. Yeah? And so for every x, we can ask about the distance for that point on the ellipse defined by the x away from minus 1, 0. Right, this point here, minus 1, 0. Yeah? And that thing will depend just on x, and it's given explicitly by this formula. Yeah? So as we move x, we get these points, these mirrored points, yeah? And we want to find the point on the ellipse, or the points on the ellipse that maximize this distance, and we're sure we can do this by this procedure because every single point on the ellipse will be recovered from these formulae. Yeah? So by just moving x between minus 1 and 1, we're moving those points around the ellipse, yeah? And we will find the thing that maximizes this distance, which is given by this formula, and it just depends on x. So we reduced this difficult-looking problem of 2 variables into a problem of 1 variable, and now it's actually an easy problem, because look at this. This just becomes a quadratic, right? So let's expand this out. And what we get, just plus 2x, and then we just plus 5. Yeah? Cool. So our task now is a very routine one, because we just have to maximize this continuous function over a closed interval from minus 1 to 1. And we will find the maximum that we're looking for. Yeah? And we have a tool to do this. I mean, we've learned how to do this. This is the closed interval method. Yeah? But before we start to use it, we're going to think about what this function looks like. Well, this is a quadratic, right? So what is the graph of D? It is a quadratic, so I don't care where it's centered too much, but all I do care about is it goes down like this. Yeah? So this guy, yeah, as we can see, a quadratic which is curving down is going to have just one maximum. Yeah? And that maximum will occur at its one critical point. Yeah? So we should be feeling now is certain kind of optimism, because we know that we don't have to care about the endpoints. The absolute global maximum of this thing will occur at its one critical point, yeah, if that critical point is inside our interval, and that's what we need to check out. So let's find that critical point. Shouldn't be saying critical number. Let's find that critical number, and let's just differentiate. So find critical number. So critical numbers, again, are where the derivative is 0 or it doesn't exist. This is a differentiable function, so it's just where the derivative doesn't exist. This is equal to 0, which is equivalent to minus 6x is equal to 2, which is equivalent to x equals 1 over 3, which is indeed inside our interval, right? So it's around here, say. So this is 1 over 3. Yeah? So we know from our pictures, we expect this to be the absolute max of D. But let's just nail it down in case anybody complains that we don't have a full argument. So what could we do? Well, we could just check the endpoints. We could check minus 1 and 1. Those are the only other two possibilities, right? That's the closed interval method. Put minus 1 and 1 into this expression. Or we could just look at the derivative, because if we look at the derivative, we see from this the derivative is positive before the critical point, then it's negative, right? So if something is positive, then negative, then at the critical point, it has to be the global maximum, yeah, just from the picture. So let's check the derivative. So check, or check the sign of the derivative. Yeah, so it only changes sign at a third. So the sign of the derivative, let's draw a picture over here. The sign of the derivative is not changing sign from minus infinity to a third, so it's either positive or negative here, or from a third to infinity. So we only need to put any number from minus infinity to a third into d prime to know the sign of d prime onto this. Yeah? So a natural number to put in would just be what? Where's our expression? Here's our expression. No, I didn't write it. Yeah, so d prime is this is what I did too fast. This, and then this thing is minus 6x plus 2. So if we just put in d prime of 0, we just get 2. So then this is here at 0, so it's going to be positive from minus infinity to 3. Yeah? And if we put in, we can put any number bigger than a third into this to find the sign on the other side. Let's put in 1. The prime of 1 is minus 4, so therefore it's negative here. Huh? This is what we expect. This is what we see from the picture anyway. So again, confirming stuff with the pictures at all stages. So the prime of x is bigger than 0 for x which is less than 1 over 3, and the prime of x is less than 0 for x which is bigger than 1 over 3. So D has global maximum at 1 over 3. So this is the global version of the first derivative test, right? Cool. So we have now justified that the global maximum occurs when x is a third. Yeah? Cool. All right, but we also have to find the distance. Yeah, we need to find the distance from this point to this point when x is a third. And that's just a matter of putting the numbers in, right? Because this thing, we can pick either y, solve for the y. So if x is 1 over 3, then y is equal to the square root of 4 minus 4 over 9. Put the same thing over 9, it's like 36 over 9. All right, so that's like me 32 over 9. So there's a square root of 32 over 9. And that is like root 2 times 4 over 3. Yeah, because 32 is 16 times 2, and square root of 16 is 4. And there we go. So that is the y. Yeah, and now to find the actual distance, we just use we can just use our function d, but we have to remember that d is the distance squared, so we need to square root it. So this is this thing, we should maybe complete it. So this is one of the points. So points that maximize distance, max the distance, are these 2 points, 1 over 3 to 4 over 3, and the other guy 1 over 3 and then minus over 3, like this. These are our 2 points, but we actually want the number for what the distance is, so let us just put it into D. Let's do it over here. And we just need to take the square root of d to a third, but let's find out what d to a third is first. So what's that going to be? That's going to be minus 3 over 9 plus 2 over 3 plus 5 minus 1 over 3 plus 2 over 3 plus 15 over 3. So that is 16 over 3. And I'm going to take the square root of this. And that's going to be 4 over root 3. And that should be the answer. Okay, cool. So that is our longest problem. All right. So as you should know by now, the midterms consist of 80 to 90% routine questions. standard routine questions. And to do well, the main thing you need to be able to do is to just get out the answer correctly in the time you have. And to be able to do that is just a matter of practice. So if you invest the time and you practice and you're able to do these routine questions and get them right 9 times out of 10, then you will do very well in the exam. There will just be a couple of tricky questions to distinguish the B students from the A students. This would be one of them, perhaps. And that requires a bit more work. That requires getting a high level of understanding. But to just do well, get a decent grade, it's just a matter of investing the time and practicing it. And you can know what you're going to do before you enter that exam. If you put that time in, if you've focused on your weaknesses, if you've done the ordered exercises at the end of the book on the sections you find difficult, you will be in good shape. And please do that. Please know the practice exam completely and do the 2 posted past exams as well. Do them under exam conditions to see how ready you are. Invest the time and then you will have the result in the midterm. I have a final office hour before the exam on Monday afternoon. Use that office hour with any final questions you have. Otherwise, I will see you either on the Monday or the Wednesday class. Have a great weekend. See you next week.